we are bringing Dan, and Dan from you are okay, excellent, very good. But thank you very much. So we'll let you carry on.
Have fun.
Well, thank you very much. And Dan,
Yes, sir.
let's saddle up and ride. What do you think?
Okay. Yeah, I like
We
that.
can talk about this stuff later on.
Yeah. We'll talk about the other things we like to do another day.
Exactly.
Yeah.
Well, look, buddy, I mean, we've already kind of like did a little pre-run, and we'll have a pretty good idea that you're going to show us some stuff that your company prides himself on. And this is just kind of, this is just the tip of the iceberg. Let's put it that way.
Yeah, it really is. I struggled putting this together, trying to whittle it down to only 25 or 30 minutes.
Well,
So
let's don't waste our time. Jump right in there and amaze us, please, because I understand where you're coming from.
Okay, let me try and share my screen here.
You got it.
Do I? Okay.
Yep.
I can't tell on my end, so I'll take your word for it.
No, it looks good.
Okay. All right. Well, what I'm going to talk about today is a little bit about what our company does in virtual engineering in the product development process. And I'm applying this here to performance engine and vehicle systems. That's probably primarily who our audience, our viewers are, but we work in lots of industries. I'll start out with a little profile of EngSim. Most of you probably haven't heard of this, so I'm just going to talk really briefly about that and some of the technology domains that we play in here, and a little bit about why do we even bother with virtual engineering, the tools that we have, and hopefully I'll have a lot of time. If I do everything else quickly, I can go through some really cool case studies, and then I'll wrap up with a little bit of my own opinion about the outlook of this. So a little bit about EngSim company. We've been around since 2003. I mean, the principals in the company, including me, have been doing this a lot longer than since 2003, but I've been with the company since 2012. But I've been doing this kind of work for a long time. In the engine, primarily in the engine and powertrain areas of the industry. We work with automotive OEs, tier ones, industrial companies, off-road companies, consumer products, and then the performance industries more and more lately. And then for many of our clients, EngSim is their virtual engineering department, and the pun is intended there. Some of the large companies we work for, they have these same tools we have. They do the same kind of work, but sometimes they just don't have the capacity or the time. And so we'll step in and help supplement those departments with either some special skills or just extra capacity. And then a lot of our clients are actually very small companies that don't have any engineering department at all. And we step in there and basically become their virtual engineering department and apply these tools to help them solve their problems. The areas of technology that we work in, we can generally categorize it in these six areas. I'm not going to go through this slide in great detail, but it's basically engines, your standard vehicles that you and I would most usually think about. We've been doing more and more in electrification of vehicles, Valvetrain, thermal systems, and then kind of crossing all those barriers. We do a lot in the 3D fluid dynamics also. And sometimes the projects are just one of these areas, like maybe just an engine project or just a Valvetrain project, but more often than not, we integrate a lot of these where I may do a Valvetrain model and a charge air cooler model and put them in an engine model, which goes into a vehicle model. So a lot of times we bundle all these together to come up with one big solution for a number of problems. But you got to ask yourself, well, why do we even bother with this? These virtual simulations, and I never try and advocate this to replace good design and testing. Where it's best used is to supplement good design and testing to make that more targeted, to save you time and cost, and very importantly, to improve understanding. A lot of times in general testing, you can come up with good solid results, but you really don't know why. So these kinds of tools help you kind of dive deeper into the solution and understand, well, why is this not good, or why is this good? So in the end, you can take those thousands of crazy ideas that you have, and you can filter them down into just a few reasonable ones that you go on with your design, and you verify that with your physical testing. And there's lots of tools out there, lots of computer-based tools out there to help you pick from that. I'm going to talk about a couple of them only. I guess I got to clarify. Sometimes people get confused that we sell software. We don't actually sell software. We use software to solve people's problems. And I'm going to just illustrate here just two of the softwares that we would typically use. And the first one is called GT Suite. It's supported by a company called Gaia Technologies, and it's what we use day in and day out for our 1D modeling. They're a worldwide market leader. It's all physics-based, a very, very stable platform. It runs on my PC. I just have a kind of a high-end PC, and I can run it very easily right here at my kitchen table. The company provides a lot of continued rapid development with this, and they got great customer support. I've known the people who started the company since the 1990s, I guess, is when they started, when Gamma Technologies first started. Some of those people have since retired, but I've known them forever and ever. So we have a really good relationship with this company. And like I touched on a couple of slides ago, this software, you can integrate a lot of these multi-physics platforms with flow, acoustics, thermal, mechanical, chemistry, electrical. I'll show a little bit about that in a few minutes. And it's got some really good pre and post processing to prepare your models and then to look at the results. And then I'll jump down to the bottom here. It couples really well to third party if you want to integrate it with CFD, with 3D flow, and with engine control software. You can actually use this to do calibration development. And that's really a big growing area for us, is helping people either in their dyno or in their vehicles do calibration development. We can become a virtual engine. On the 3D side, looking at CFD, computational fluid dynamics, software we really like is called Converge. Sometimes we'll look at AVL Fire, but Converge is really, their specialty is really doing flow through engines. They're really good at moving, we call it moving meshes, but you actually have to, you mesh the piston and you mesh the cylinder and the cylinder head and valves. And you can actually move all those relative to each other. So you can make a fully transient flow. You can do steady flow, but where it really shines is doing the transient flow with moving pistons and valves and things like that. Rotating machinery like turbochargers, it's really good at. For doing exhaust after treatment, that's where the AVL software is a little bit better at. We don't do a lot of that kind of work, but most of our work is doing in-cylinder 3D CFD. Again, this has really good pre and post processing for building your models and looking at the results. And it's really good at distributed computing. You can run it on multiple CPUs. A lot of the work we do up in the cloud. So I do all the preparation on my laptop, and then I throw it up in the cloud. Go have lunch, come back, the problem solved, and I download it from the cloud and look at it. And it couples really well to some other third-party software, like GT Suite. We can embed a 3D model inside a GT Suite engine model. Okay, some of the case studies I want to talk about. This first one kind of illustrates the engine modeling and a little bit of the Valvetrain work. The purpose of this particular example is to build an engine model that I can use for a variety of subsystem and then component design studies. And the three I kind of picked from our portfolio to talk about today was a V8 intake manifold. I looked at the difference between a dual plane and a man-feed plenum, a cam timing study, and a port flow study. But those might be interesting to a lot of people that might be here today. This is a bit of a eye chart, I'm sure, but the big diagram kind of in the center to the right is what the engine model looks like in GT Suite. What I have illustrated in the box in the center is a dual plane manifold, and that comes from. We start with the CAD model shown on the left, upper left. From the CAD model, we pull an air core model of the flow path through the model, and then we pre-process that in GT Suite with a module they call Gem 3D, and that discretizes the model, and then from that we can export that into the GT Suite model that you see on the right-hand side. And it kind of looks like a spider web in the middle, but that's because the flow path in a dual plane manifold is kind of complicated, and we can address that. All those little boxes you see on there are what we call objects, and all those objects, it's a flow path of like a pipe, or it's a plenum, or if it's an orifice, or we have cylinders, and then we have on the exhaust side, we have collectors made up of pipes. On the intake side, we put an air cleaner on here. So that's kind of the way this whole model is constructed, piece by piece, like that. And a lot of it can be automated with the preprocessors. Similarly, an in-feed manifold, I pulled up this example because here's one where I did not have CAD model. I'm not always lucky enough to have CAD data from our clients, but the geometry was simple enough where I could build the model just from my experience and what we knew about the inside, we could look at the model, or look at the part, actual part, and make some measurements and come up with a really good approximation of what that manifold looked like. And you can see it's a lot simpler model to build. The flow path is a lot simpler. Now, the kind of results, the overall results we would get from that, there's lots of overall results. The two I'm showing here is just basically power and torque. You can show that when everything else is equal, the power advantage went to the in-feed manifold, shown in the red lines, power on the left, torque on the right. And that's good to know. I mean, we want to know which one's better, but we ask ourselves, well, why is one better than the other? And so that takes us to where these tools are really useful, where I can pick it apart, pick the results apart, and look at the results cylinder by cylinder. And these two charts it's torque. The one in the center of the page is the in-feed manifold. The one on the right-hand side is the dual plane manifold, and this is volumetric efficiency for each cylinder in that D8 model. You can see, at peak VE, it varies as much as 11% on the in-feed manifold. On the dual plane manifold, it varies 9%. But the averages on the average of the in-feed, even though that band looks wider on the in-feed, that pulls the average up. So you're about an average of 96.5% VE and 88.9% on the dual plane. So that kind of explains why one is better than the other. And it also illustrates a cylinder to cylinder problem that you probably want to resolve with this too, with some further development.
And that's all been being done through your computer simulation. Yeah.
This is all part of all the results you kind of get. You can, if you go back to one of these models here, I can put every one of those little boxes in there of a pipe or a plenum. I can go look at anything in there, pressure, velocity, temperature, whatever, and look at the wave dynamics at a particular RPM. So you can go in there and interrogate exactly where you want to look at some special problem or question. Another thing that this is really good at is looking at cams. This particular, I use that same engine model that we just looked at, and I looked at set up a DOE sweep and exhaust cam lobe timing and intake cam lobe timing separately from each other. So there's 150 runs in this. They're unique runs, and I could run this, and this might take me, I don't know, half an hour to run on my computer. And so you can imagine how long that would take you on dynos, and how many camshafts you'd have to build, and how much dyno fuel you'd burn, and how much at risk you would put your dyno engine to blowing up. I don't worry about blowing up engines here or burning fuel. So this really quickly zeroes in on the best timing options for power and torque. And to no surprise, if you're in the engine business, I mean, the best timing for best torque and best timing for best power is going to be different. And you can see on the left-hand contour plot, it wants one particular exhaust lobe timing and a particular intake lobe timing, and they're different for the best power at 6,400 RPM. So you can make those trade-offs consciously without going and making 150 dyno runs. So you take those 150 runs and maybe boil it down to 2 or 3 camshafts that you actually have to go grind and run on the dyno to verify. So that's where the economy really is in this. And you can also look at some tricks with staggered lobes maybe that might help you solve some of those cylinder to cylinder issues. Another thing you could use this model for is looking at port flow in this case. I mean, when I kind of started in this business, I worked at General Motors for quite a while in doing cylinder heads and port development. And I always had a question about, well, where do I want to improve ports? Because sometimes it's a trade-off. You don't just want a big monster port. Don't want good high lift flow. Don't want good low lift flow. Well, here I didn't build flow models and test them on a flow bench. I just made up these flow curves. I had a baseline flow curve. I just said, well, what if I increase the high lift by 10% or the low lift by 10% on the intake or exhaust, and I just run them through this model and see, well, where does the engine really want my flow development at? And it told me that the high lift intake flow is probably more valuable than anything else. So if I'm going to prioritize my physical testing, that's probably where I want to put my effort. And another kind of a tangent on that, this is one of my favorite plots that comes out of this 1D work, is looking at mass flow through a port overlaid on the cam lobes. The question always comes up again, like high lift or low lift, and this kind of explains why. Look at the left-hand plot. This is 4,800 RPM. The red curves, that's the exhaust side. The solid line is mass flow, and the dotted line is exhaust cam lobe. And what this tells you is that when you have the blowdown on the exhaust side, you have an immediate spike of when that cylinder pressure is kind of blowing off into the exhaust port. You have a lot of mass flow at very low lifts. So this would explain to me, well, I want to put my effort on low lift exhaust. And then you look at the blue lines and it shows, well, there, the peak mass flow on the intake is at peak cam lobe, cam lift, or valve lift. So that explains the previous chart about, well, this is why you want to put most of your effort on the intake side at high lift. And then the other side note on this is that it also shows your overlap where, okay, at this 4,800 RPM, these cams don't look timed really, really well to me, because you'll see all that flow reversion where you have those little backwards blips, both at overlap and then at intake valve closing. You have a lot of reversion on the intake port. So if you were to retime the cams and go look at this plot again, if you retime the cams to a better position, then you'd probably see those minimized. And that's, I couldn't imagine trying to do this on a dyno engine. I mean, you could do it if you got some pretty sophisticated pressure measurements and high speed data acquisition, but I didn't have to do that here. Next example I wanted to show you was Valvetrain, where we can do some modeling on Valvetrain all by itself, whether it's integrated into an engine model or not. And for this, we're looking at the current client's profile, and then we're going to offer some suggestions on improvements. This is just a pretty common Valvetrain, push rod Valvetrain, looking at the kinematic model and the dynamic model. This is how we start on the left-hand side, typical push rod CAD data. We build kind of a GT design model. GT design is the CAM design or the Valvetrain design module in GT Suite. And then from that, if you go down to the lower right, it'll give us some of the basic kinematic. You see some of the problems if you're a Valvetrain guy. You can look at these and say, "Oh, this is kind of messed up." And that's kind of the point, is that this was the baseline CAM that we were given to evaluate and to offer some suggestions. You see lift and velocity and acceleration and jerk and some radius of curvature issues. And then from that, we can go and build a system model you see in the upper right-hand side, where we actually put together several of these. There's an intake and an exhaust valve in this model on a camshaft, and we can go and duplicate this several times and build a whole complete V8 model. So you could look at the whole torsional effects on the camshaft or the timing drive, as well as the dynamic effects of the springs or valves. So that takes us to this chart where that system model, you can look at.
Hey, Dan.
Float. Yes, sir.
Dan, let me interrupt you 1 second here. You're going in and out a little bit on your microphone. It's getting a little gargly. A moment ago, it was perfectly clear. And then when you started a second ago and went back the other way, you've done it a couple of times. I just wanted to let you know that if there's something to do where your microphone is or anything like that, you might want to check it real quick.
Okay, well, I'll make sure I stay pointed at my computer. Yeah, let me know if that happens again.
No, that sounds clear right there. Thank you.
Okay, I'll stay pointed right at my computer rather than looking out the window while I'm talking. There were some white-tailed deer running across my backyard, so I think I got distracted.
Yeah. All right.
Okay. Well, here, look at the big chart in the middle is looking at the dynamic valve lift, and you can see some issues if you really look carefully. If your screen's big enough, you can see some problems compared with the intended valve lift and the actual dynamic valve lift. You see some bounce at the closing. You see some problems over the nose. So that's the kind of things we're looking for. And then looking at the chart on the right-hand side, you're looking at spring margin. The spring margin looks okay. Wasn't really a whole lot I needed to do there. But we're also looking at some of the hurt stresses, which if you're a camshaft materials guy, that's going to be really important to you to make sure you stay within some ranges on that. So those are the kinds of things you can look at this with the Valvetrain module in this GT Suite software package. And this is probably one of the areas that I do a lot of in the company is the Valvetrains, as well as those engine models that we showed before.
Right.
And I can take this Valvetrain model and I can actually embed it in the engine model and run a dynamic valve lift rather than just a kinematic valve lift. And I know, I mean, Jeff, you've been working on NASCAR engines a long time. That's kind of a big deal to be able to look. That was a big aha moment years ago when they discovered we should be looking at dynamic valve lift and not the static valve lift.
No, that's why I say, and the ability to be able to go back and make subtle changes in minutes instead of days.
Yes, exactly. And not break hardware in the meantime.
Exactly.
Okay. This case study is a 3D port model where we're looking at some flow, and there's two cases here. We're looking at a double red cam intake and exhaust port flow, steady flow, and then I got a quick example of some fully transient flow here. Try and speed up here because I might be getting close on time. But we start with a CAD model. In the center there, we pull an air core model out of it, and from that we mesh it into an intake and exhaust model. And then on the far right, I actually added some plenums on it. So this 3D CFD model kind of simulates what you would see in a flow bench. It was kind of the purpose of this study was to duplicate a flow bench. And then on the intake model, you see that little gray section of the cylinder. That's where we can actually evaluate the in-cylinder mixture motion, looking at swirl or tumble. We've been trying to do that for years and years on a steady flow bench without a whole lot of success. And this is a way we can look at that a little bit more accurately. And this is kind of the result. I'm not going to go through these results in detail, but I wanted to highlight that we can calculate the flow capacity, just like you get a flow bench. And then we can also look at the swirl and tumble. And here we're quantifying it in angular momentum flux, which.
Dan, you're doing it again. Whatever's going on, you're doing.
All right. Try and be more careful here. So the numbers on the right-hand side are basically, we're looking at the swirl and tumble quantifications in that little gray cylinder. And then real useful out of this is I'll sit down with the guy that's working on the flow bench to show him these, and it's really pretty enlightening to be able to actually see the flow. This is at 3 millimeters of lift on the intake port. And you can see what's going on where you have a lot of flow separation and problems right there at the seat interface. And then similarly on the exhaust, this is at 6 millimeters on the exhaust. And you can see one of the problems here. This illustrates one of the problems you have doing this on a flow bench. Where that exhaust port, you don't have an exhaust manifold on here, you're just dumping the flow into the room, and it's not very realistic. So this kind of illustrated a problem that a lot of us are going to see on the flow bench, and why you want to do this work on a flow bench with a manifold on, or at least a pipe extension. And this is, hopefully this will come through here. I'm going to try and run this video here. This is a case, this was a little generator engine that we did. This is where we go like all in with this transient analysis, where we're looking at the cold flow of the intake stroke, and then we're actually compressing it. And then in the end, we're actually lighting the spark plug and combusting it and looking at the flame growth. And so you get some good quantitative results, but you also get good qualitative results for looking at how the flame propagates, and if it's going in. You don't want to be blowing it at the wall, and this will show you that. This looks like pretty good flame propagation to me. It's starting on the side and growing across the side, so that looks pretty good. Does that come through in the video, Jeff?
Yes, it does. Yes, it does.
Good.
And I'm not trying to rush you, but how much more you got on your little presentation?
I just got a couple of slides. I think I'm just about there.
All right.
Okay, the electric vehicles, we're doing more and more of this, and I guess I wanted to bring this up, and just a quick editorial here, that you can appreciate electric vehicles or not. The racing industry, in my opinion, and the major sanctioning bodies really need to embrace this whole movement to EVs to some degree, to keep the racing relevant to the OEs. And then tools like this allow them to actually investigate that. What the best path forward to try and incorporate EVs to some degree, one degree or another, in the future. And I got two real quick pictures here on some EVs. This is a standard ICE engine in a vehicle. You can get these kinds of results. This was just a simple quarter-mile drive cycle. And then this is actually a hybrid electric, where we actually build an engine model embedded in the vehicle, and then also included electric motors at the wheels. So we can look at this either way, or any combination of one or the other. And then I'll just wrap up here with my outlook and summary, is that these tools are just like, they're growing like crazy. They're growing so fast in capability and where you use them, that it's getting very hard to even for us to catch up and keep up with it. But I think you're going to be seeing more and more of this, more and more integrating of these models, and you're going to see more and more use of this over in the near future. So, so I welcome your feedback, and I'd love to be able to come back to EPARTRADE in the future, maybe, and take some deeper dives where I can spend some more time on any one of these technology domain areas. So I guess I'll just wrap up there. I don't know if you had any other questions, Jeff, or if anybody else, I can certainly try in the brief moment.
Somebody made a comment in the chat button. Cool stuff. So, and definitely we'd have to have you on a Wednesday for a longer period of time.
Yeah, I'll get you there for a 50-minute show, and get an opportunity to be able to clean up a little bit of the audio, just so you know ahead of time, and and we'll be able to do a better job for you all the way around. But it's really impressive, like you and I were talking before you came on. This is the way of the future. Your company looks like they've got it figured out, and I love the fact, again, as a gearhead, I don't want to spend a month doing something that I can get done in days, and I don't want to be doing something in days that I can get done in hours.
Yes,
So that's the
absolutely.
thing I see. It's the time saver, and it's going to give you information, that same day. So I think it's a great concept.
Yep.
Thank you very much, Dan.
Okay.
I need to carry on as
Yep,
it's
of
already
course.
3 p.m. So we're going to thank you very much for your presentation, and we'll have you back during our weekly webinar series, definitively for a more in-depth
Sure.
tech webinar.
Registering on EPARTRADE is easy. To start, click on the Join for Free button on the homepage. First, search your company to see if it's already in our database. If you see your company on the list, click on it to select it. Then, choose Claim Company if you are one of the decision makers, an owner, marketing person, or main company contact. Or choose Join Company if you are an employee, and press Continue. If you couldn't find your company in our database, select Register a New Company. On the following page, fill out your name, email, phone number, job title, and choose a secure password. If you chose Register a New Company, you'll need to choose your business type. Select Supplier if you're looking to display products or services and connect with buyers. Choose Racing Business if you're looking to source new parts and connect with suppliers. Choose Race Team if you own or are a member of a professional race team. Then, enter your company name. Please provide a website, Facebook page, or LinkedIn if you have one, and choose to either claim or join the company. You can view and agree to our terms of use here. If you'd like to receive our weekly newsletter, choose Accept. Finally, click Register Now and your registration will be submitted for approval. An email will be sent to your inbox. Please confirm your email address and you will be approved shortly. Welcome to EPARTRADE.